Hello, welcome. We're the Biojacks, and this is a summary paraphrasing our past few months working on our device. This is a team. We have a pretty diverse set of skills that we can use. Um, and this is the overview of what the presentation is going to look like. We're going to tell you about the background of the fields. We're going to go through the iterative process of designing the device and then testing it, and we'll conclude with some analysis. $26 billion. So this is the market the value of the market for animal research. And the problem, though, is that animals, as been noted by our esteemed faculty, animal models are kind of the comparisons between animals, their models, and humans kind of incongruent. You have some pretty staggering statistics. 90% of animal tests fail to lead to human treatments. You've got 89% of animal studies cannot be reproduced. You've got other things, and here are some trials that actually were pretty terrible. You had, in this trial, the TGN 1412 trial, you had 6 out of the 8 volunteers suffer from severe multi-organ failure. And then just in general, when we depend on mice for neuro-based disease models, the diseases just work differently in mice than they do in humans. But what is the better type of modeling that we could use, something that could replace this kind of in vivo system, the microphysiological systems, the organ on a chip? Let's get to it. So what is a microphysiological system? It simulates these functions. It transports, filters, dilutes media, food, nutrients, and what the key components that you want to replicate in a model that you might have or a system that you might have are porous membranes that separate cell type, something to deliver media, something that constantly perfuses media, some dynamics, flow of fluid through your system. And where did this all start? Or I guess this is the end product, having not just an organ on a chip, but having an entire body on a chip. The value of the market for microfluidic devices. Now, around 2017, it was estimated at $10.8 billion. It's estimated in 2023 at $27.2 billion, over superseding the value of the animal research market. Kind of staggering. The timeline for the fields for microfabrication, microfluidics, and their respective devices kind of start with Jack Kilby when he demonstrates the first integrated circuit. And we have, because of his research, we see Silicon Valley or the Silicon Age kind of emerge. And we get these devices that are silicon-based that are actually better than macro-sized systems. They're micro-sized systems. And they deal with biomaterial quite well. They hold up in various conditions. They're pretty thermodynamically stable. But the problem is, when you analyze them under UV light, they're opaque, and you get later white side, PDMS, and then you see an evolution. Previous research with PDMS, pretty good. You have layer parastasis is kind of simulated. You have an epithelium, endothelium, and these things, and then the problems are you get some blockages with absorption and some material kind of pressing itself in your device.
Yeah, so some previous research that's been done that's relevant to our gut on a chip includes things that have been done, such as creating 3D villi in an organ on a chip, populating it with co-culture with bacteria or other like living cells, and then also different kinds of dynamics, things like peristalsis, adding flow, suction, and not suction. So all of these papers that we researched almost all of them were made of PDMS, which means that when they want to apply them for drug absorption or anything like that, they're going to be unable to do that without knowing how much is being absorbed into the PDMS. So that's one thing that we really tried to attack in our model. So I'm going to talk more about our device design. So our original design was quite different than what we ended up using, but it was a 2-layer PDMS model because we were first trying to imitate the integration between the lymphatic system and the epithelial tissue of a gut villus. And we had a lot of problems with this model. First of all, the PDMS was our layers were so thin that it was really hard to create working PDMS layers. And in addition, we were unable to culture blood and lymphatic cells in the same chamber. That was just something that fell through when we were researching. So we realized that we need a different kind of device. So for the next couple of weeks, we created this improved design. It was a 3-layer polystyrene model. It had this formula, so it had 3 layers so that we could have epithelial and lymphatic. We got rid of blood cells. We were imitating the same integration, just without the connective tissue. And some issues we ran into was first adhering the different layers together. So we finally decided on using adhesive sheets that were very thin. But another issue we ran into was with this 3-layer model, the 2 membranes were almost always going to sag and touch or contaminate each other. So we decided we probably need a 2-layer model. And then another issue that we ran into was the fact that our channel was so long. It was about 40 millimeters long. It meant that we would need a lot of media in order to feed our cells for a static device. So we realized we should probably cut that down. But first, we filed a patent to patent this design of using a non-PDMS layer design fixtured with adhesive sheets. So this is our finalized 2-channel layered polycarbonate model. We ended up using polycarbonate instead of polystyrene just based on the materials we had available in the lab. On April 13th, we were very excited to have a non-leaking device, and this is an image of it right after Amy finished testing it. So just to kind of dive into this is what our device looks like in a cross-section. So we'll talk more about assembly in the next slide, but basically we have polycarbonate layers attached with adhesive sheets with a very thin polyester membrane in between where the cells adhere. This top polycarbonate right here is just like an extra layer to keep everything sealed together. And then we have a 1/4-inch thick acrylic top piece with threaded wells that not only accommodate plenty of media for our cells, but also allow us to integrate flow if we would like to. This is, to put cells. Okay, so this is our top view of our device. And currently this is how you assemble it. So you start with a glass slide, which is good for imaging, and our entire device is clear, which is great for imaging. So this is the first layer of polycarbonate, then you add our very thin membrane, and then the next layer of polycarbonate, and then we have that top piece that seals it all together before attaching the acrylic with the wells. And this mimics, and we shortened our channel length to 1 centimeter. And so currently we are not culturing lymphatic cells just to for time reasons, but that's definitely a goal that we have in the future. But so currently we're just mimicking the gut epithelium.
Okay, so I'm going to talk a little bit more about the materials and the methods that we use. So what we decided to use is the polycarbonate sheets just because it was easily available and also because it was a lot easier to manufacture.
Speak up.
We could go through a lot of different iterations of the design very quickly, and we didn't have to wait to cure it in the way that we would have to for PDMS. And we used the adhesive sheets because it's pretty hard to solvent bond with the polycarbonate, and it just ended up being another way because we could use the same basic manufacturing method as the polycarbonate sheets, and it worked really well for what we needed it to do. So we decided to go with a slightly different membrane. It's very thin and it's also transparent, which is helpful for us for imaging because our layers are stacked vertically. So if you look at the 2 membranes here, this is a very standard membrane that's used, but it's a little bit more translucent, but ours is completely transparent. You can't actually really see it that well in this picture, but it's like right here. And so it's a lot easier to see our cells because they are on the top channel. Because we are using a non-PDMS device, we needed to find a way to interface with the actual device that would work well and kind of actually fit with our polycarbonate layers. And so we decided to do an acrylic top piece. It was made through laser cutting, and it has these threaded wells, and the wells they hold media, but you can also add attachments. So in this case, you see the little attachments over there. They're fittings that we can use to attach tubing. So in the case that we wanted to add flow, which we did try, we could do that as well. So this is our basic manufacturing process. We use the silhouette vinyl cutter with various settings to cut our membranes, our adhesive sheets, and our polycarbonate devices, and we basically just created vector files that had all of the layers that we needed for our device, cut them all out at one time, and then we can kind of go through in a machine, like assembly line type process, and put it all together. One of the problems that we ran into is because our device is not gas permeable and the adhesive seal is not totally perfect, we ended up with bubbles in our device, which is not good for our cells. So what we decided to do is basically take the devices. Well, you can see all the bubbles that are kind of in this device already, and this is our main channel, and so we were running into the problem with even once we added liquid, we were still getting a ton of bubbles in there. So what we did is we decided to take all of our devices, put them in water, and then degas them overnight, and that seemed to solve our problem with getting bubbles. And once we had done that, even if the seal wasn't totally perfect on the outside, in the middle of the channel we weren't getting any more bubbles. And then this is kind of our seeding protocol, so I'll just go through this really quickly. First we sterilized the devices, and then we decided to treat them with collagen just to help the cells grow a little bit better by creating like an extracellular matrix. And then we basically did our seeding and splitting the cells at the same time. So we washed them with PDS, and then we treated them with trypsin to help them come off of the actual bottle that we had them in. And then we filled the bottom channel with media, we diluted the cells that we were going to seed to a good density for our device, and then we put them in.
So diving into our results, the first metric that we looked at was that we were actually able to create a leak-proof device. And you can see here that when we tested it with food dye, the red and the blue only combined in the very middle where we have the membrane, there's no diffusion into the sides of the device as you might see with PDMS, because the polycarbonate does not allow for that absorption, which is definitely an advantage of using this material over PDMS. Now to show that we actually are able to seed cells successfully, here we have an image showing the two ends of our device. This top image is the right half and the bottom image is the left half. And so you can see that we have this monolayer forming here. All of this is cells. In the bottom image, these grayer areas are gaps, which they did end up later filling in. But in the beginning, we were thinking, okay, if we have these gaps, why might they be? One of the reasons could be that there's these little burrs on the side of the device in the middle channel from manufacturing. So that's definitely something that can be improved upon in next iterations. This is to show that our cells are in fact alive. They're not just dead cells forming a nice little monolayer. So everything you see in green has been stained, and these are cells that are alive. And we also had some interesting results comparing the laminate material with the polycarbonate material. So the laminate actually caused the cells to clump together, and they really did not enjoy that environment, whereas the polycarbonate formed that membrane that we were looking for. And we were thinking, okay, why could this be? One of the reasons we came up with was the laminate might be toxic to the cells, or the laminate is actually thinner. Overall, it's shorter, so that causes less room for media and for oxygen to flow, which can create a less favorable environment than the polycarbonate.
All right, so as we talked about earlier about threading the acrylic with the wells, so we were able to integrate flow into our device. So we use fittings into each of the wells and then attach the tubes. So the syringe pump over here basically feeds in the media into the device, and then it goes out into a covered petri dish, which is all kept sterile. So we calculated the flow rate that we needed based on a standard shear stress for the cells, and that was derived from a paper which is cited below, just kind of cut off. But our eventual flow rate meant that we would do 2.7 milliliters per day, which is a good amount because each of the syringes holds 10 milliliters, and we'd only have to change the media every 3 days. So after we integrated flow, we actually found some issues with leaking. So one of our potential solutions is to seal the fittings with silicone to prevent the leaking. Another reason we think this happened is because the fittings didn't actually line up with our inlets. So as you can see, this is the inlet, and this is the hole from the fitting. So we're thinking that it got clogged somehow. So we got new fittings, which you do see overlap. So we're going to try those next. And instead of pushing the media through, we're gonna try suction, which seems to work. I did some preliminary tests and they didn't leak after that. So as our conclusion, we have a fully functional device for static media. We can integrate flow potentially because we have threaded wells that can integrate the fittings, and we're working on that right now. A big benefit of our device is that it's fully imageable because every material is transparent, including the membrane, which is super transparent, and the glass cover slip, which is very thin and transparent as well. Our design is simple, so it can be quickly prototyped and assembled. So whereas PDMS, one iteration might take 3 or 4 days because you have to print it and then pour in the mold and then take that one out and then pour in a second mold, that might take several days. We can test this in 30 minutes and see if it actually works. And a big plus is also that it doesn't require special equipment. So we're basically only using a vinyl cutter for all of the layers and a laser cutter, which is easily accessible for most people, to cut the acrylic top layer. And so it's very easy for any lab to just purchase these materials and try to make our device. So our steps moving forward is for our current devices, we're going to do further tests like TIR to measure the junction dynamics of the cells. And we're also going to try to revisit our original goal of co-culturing lymphatic and epithelial cells. So right now we've already stained some lymphatic cells that we're going to see today to our devices. And again, we're going to try flow on some other devices. So under suction instead. So Timothy helped print this device for us, which caps a falcon tube so that way we can keep the media sterile as we're pulling the media out. And also to optimize manufacturing. So as we talked about before, there might have been some imperfections in the channels and how smoothly they work, but that's also because we didn't spend a lot of time optimizing how the vinyl cutter was cutting the channels. So if we spend a little bit of time on that, I'm sure we could prevent the issues with the cell adhesion to the uneven walls. So stuff that we learned from this long project. So some advice I thought was begin with the end in mind. If anyone's read the 7 Habits, it's habit number 2. So a big thing was like planning ahead and making sure that what we were doing at the current moment wasn't unnecessary, because even if it worked in the end, if it didn't fit in with the overall project, then it was kind of a waste of time.
Something I learned was that a lot of times simpler is more effective. So when we had some issues, picking kind of maybe the less complicated route actually ended up working better. And especially keeping in mind all the time constraints and material constraints that you have is super important in the design process.
I thought you should learn from the past, just making sure to document everything. Definitely, it's very much an iterative process, even in a biology lab. So the more notes you have, the easier it is to go back and iterate better in the future.
Don't be afraid to ask questions. You can definitely get bogged down by the fact that you don't know that much, especially when you're part of a team with a diverse skill set. So it's just, if you're afraid or you're nervous, just think of it as utilizing all the resources at your disposal.
I said start early and come in often. I think one of the reasons that our device works so well is because we spent so much time just like figuring out what worked and what didn't, and so doing that early enough in the process helped us like have greater success later on in the semester.
So just some quick acknowledgements that helped make this project possible. So obviously Timothy, and Becca, and then also Linda Griffith and the Griffith Lab. And BioRender is how we made a lot of our